Great. So let's start with chapter 1, where he's going to lay out some of the core ideas of what pattern recognition, machine learning, this book we're reading about, is all about. Some of the core terminology topics that we're going to be covering in the rest of the book. So at the beginning, he just talks about searching for patterns in data, why that's important. And there's a cool example of this that happened in the 16th century, where this very wealthy Danish guy who was a big astronomy enthusiast, he had an observatory, and he took had people take very precise measurements of the orbits of the planets and astronomical bodies. And those very precise measurements later then helped Kepler come up with Kepler's laws of motion, of planetary motion, upon which then Newton built his laws of universal gravitation, and this kind of led to the development of mechanics, calculus, much of the math that we're actually going to be using in this book. So gathering data, but also then finding regularities in data is a really important topic that's led to lots of developments, and that's kind of what we're going to be thinking about in this book. Now, the key aspect here is that we're going to be looking at the automatic discovery of regularities. So we're going to be designing algorithms that will find patterns in data for us. So Kepler, for example, he had to kind of look at this data and think about the regularities that could be there. But we're going to be designing algorithms that try to find these things for us. Now, interestingly, and I really like that Bishop emphasizes this. So it's we're going to be interested not just in discovering these regularities, but also taking actions. Once we have these regularities. So once you discover these patterns in the data, what to do with them? Should you classify this as as a planet? Should you say that the planet is going to be in a particular place? And there's going to be a really interesting interplay between probabilistic concepts that help you to characterize uncertainty and your knowledge about a situation, with concepts from decision theory. So how much it costs to get a decision wrong, and that interplay can tell you what information is worth gathering and how to best apply it. So that's kind of a lot of the stuff that's going to be coming up in the book. Okay, now a very important example, and if you know anything about machine learning or you're interested in it at all, there's this idea of recognizing handwritten digits. And so I think back, I don't know, I guess in the 70s, 80s, maybe even before, there was the idea of applying computers to the task of recognizing handwritten digits. And why do you want to do that? Well, it's because people were, sending mail, and it would be really useful to have a system that could just read, the backs of envelopes and tell where mail was going. So this problem, handwritten digit recognition, became really important and is really practically important, and that's kind of the basic benchmark that people use. If you've heard of this data set called MNIST of handwritten digits, that's what it was all developed about. So having lots of examples of digits that then we could train algorithms to help us recognize. So yeah, so let's get back to the problem. So we've got these handwritten digits, and they're 28 by 28 pixel images. And the goal is we want to build this machine that will take one of those images and give an answer 0 to 9. And as he points out, this is a non-trivial problem because, people aren't robots. So everyone writes their zeros and ones and twos in a different way. So it's important to be able to deal with that variability. So, how do we deal with that variability? So one possibility, and before we get onto that, here is kind of an example of, what some of those digits look like. And okay, if everyone wrote their zeros in exactly this way, it would be no problem. You could just match for this exact pattern. But of course, people write their zeros all differently, their ones differently. So that's why it's important to be able to handle that variability. Now, back in the early days of AI, one way people might have approached this problem is through setting up just systems of rules. So the kind of rule-based AI was very big in the early days, and it's still around, and I think there probably are applications where it's really the perfect thing to do. But for applications like this, where we're dealing with, let's say, more like kind of organic data, it seems intuitive that a rule-based system wouldn't necessarily work, because how would you be able to capture all possible variations in zeros? Like even in this particular example, right, we have kind of a 0, but maybe is it a 0? Maybe it's actually kind of a 6, and there's other things. What is this? Is that a 5? Like it looks like a 5, but it could be something else. Or look at even these two examples. That's a 3, but maybe it's like an 8, and the person didn't fill it in right. and trying to capture that with large systems of rules doesn't seem appropriate for this particular kind of problem. So as Bishop says, it's going to lead to a proliferation of rules and exceptions to the rules, and that's just going to become really really difficult to build and difficult to debug in a reasonable way. So for problems like this, it's much better, and you can get much better results. And in fact, this has now become a benchmark. This MNIST data set, recognizing these digits, is now a benchmark of modern AI systems. To adopt the machine learning approach. So we just, instead of trying to build in the rules, like going in and telling it, well, if you have a line that's kind of going in this direction, it's probably a 1. You just prepare first a training set. So a training set of examples of lots of zeros and lots of ones and lots of all the digits along, and with each example training set you also have a kind of target vector, or just some label that tells you which kind of digit it is. And the idea is to essentially be able to build an algorithm that will take this training set and these targets and figure out the regularities that are there without you having to tell it. So building systems that can figure out these regularities so that its output will then tend to be correct, and we'll give it we'll give it a new digit, and it will tend to classify it correctly the way that maybe a human would do that. So the result of running the machine learning algorithm can be expressed as a function y of x, which takes a new image and outputs a vector telling you what the digit's supposed to be. And so how do we figure this out? So this happens during a training phase, which is also known as learning, where the system somehow, and the whole big chunk of the book is about exactly how this happens, but it will go from those examples that you've shown it and the labels, and try to figure out how to match what the regularities are that map those training examples to the labels you've given. And once you've trained this model, how do you evaluate it? Well, these models can be very sophisticated, so in some senses, sometimes they can even memorize your entire training set. So it doesn't necessarily, it's not very useful to test the models on the same data. So what we often do is we hold out some of the data from training into what's called a test set, and then we evaluate the performance on this held out data, so that the model doesn't have a chance of just memorizing its examples. And this is a really important property that we want, which is kind of generalization. And why do we, generalizing from the training set to held out data to data in the real world? Because we don't really care actually. We already have the labels for the training set, so we don't really care about classifying that data. The point is, when new people write their digits, how are those going to be classified correctly? So that's kind of what the whole game is about. So generalization is kind of a central goal of pattern recognition, which is the case. Okay, so the next step. So once you're trying to build one of these systems, there's often a step of pre-processing the data. So those digits that we had, they don't arrive. They just arrive as 28 by 28 pixels. But often that's not the most useful format of dealing with that data. So you might, for example, take these images and say, okay, well, it's going to be really useful to take these pixels and maybe figure out where how many edges like that they contain, or do they have any loops, or even something more basic, just taking these images and kind of centering them so that this 7 appears in the center of the image rather than on the side. So reducing some of the variability. And that's really important because, and often, when we're looking at these problems, a difficulty that we have is our brain does so much pattern recognition and pre-processing already that we're like, well, obviously this is kind of a very simple problem to solve. To the extent that actually, in 1956, one of these very first AI conferences, they decided that they were going to give the problem of vision to a grad student to solve over the summer. So, it's not just us, us novices, that when we're looking at this thinking it's an easy problem. Even like, the great scientists of the time were thinking, oh yeah, like vision's simple. Like you just, find these patterns, it's easy enough. A grad student will solve in the summer. And here we are, more than 60, 70 years later, and okay, we now have systems that are solving vision at reasonable ways, and we still don't really understand how they work. We just have systems that can actually do the problem. So it took a long time, and a lot of the techniques in this book kind of give you a sense of what's required. But yeah, so the very first step of machine learning algorithms often is kind of pre-processing step. of taking your data and putting it in a format that's more useful, or in which the pattern recognition problem will be easier to solve. So that's kind of what we're talking about here, which is exactly, so transform them into some new space of variables where it's hoped that the problem will be easier to solve. So that's the whole point. And this is kind of often called, feature extraction. So as we said, with the digits, after you center them, maybe you want to start looking for loops that might be useful features for determining whether something is an 8 or a 6 or not. Another aspect of this preprocessing is indeed to speed up the computation. So you might not want to work with the entire 784 set of pixels. It might be simpler to reduce that somehow. So essentially, the game is going to be to find these useful features that are fast to compute, but are still preserving the information you need for discrimination. Because of course we can just zero out all the features, and that's fast to compute, but obviously all the information is gone. And so and part of this process, will essentially can result in having fewer features to work with than the raw pixels that you started with. So that can be kind of a case of dimensionality reduction, going from your large pixel space all the way down to a limited set of small but useful features with which you can work. So that's often the first step. Okay, so now we're going to talk about kind of some of the different types of kind of learning problems that we're going to come across. The type we've been talking about so far is supervised learning, and it's called supervised learning because for each one of your training examples, you actually have a label, and the whole game is to figure out the regularities to take you from the training examples to the labels. So it's supervised in that someone, a supervisor, has given you a label for every one of the elements in your data set. Now, the type of problem we've talked about, where you have a kind of a discrete number of categories you choose from, that's typically called classification. So you're classifying, those digits, those pictures, those handwritten digits into a number from 0 to 9. It might be there might be pictures of birds. You want to tell which kind of bird it is. So those are all classification problems. We're trying to classify an input into one of a discrete number of categories. Another really important class is regression, where the output is actually kind of more continuous. So for example, let's say you want to know what is the particular price of a stock tomorrow. So that's not a number of 1 to 9. It's basically has a continuous value. So that's an example of what's called a regression problem. But again, what makes the most supervised learning is that in that stock example, you will have, let's say, historical data that has said that, well, when all these important economic parameters are moving a certain way, the stock price was so and so the next day, and you have like a history of that of that data, and then you want to now know tomorrow what is going to be that stock price. So the supervision is in the fact that you have historical data with labels of some kind. The other very important class of machine learning pattern recognition problems is unsupervised learning. I don't know why I keep switching to these to the eraser, but unsupervised learning. And that's where the data doesn't come with labels. So you have to kind of learn, that's more about finding regularities in the structure of the data itself. So for example, you might be looking for clusters in the data. The data is often not randomly distributed in the feature space. Actually, it is bulking together in certain parts, and that's going to be really useful information. Maybe you could use that later on to perform a classification. You might actually want to just model the distribution of data in that space. So that's kind of density estimation. How I have you pretend that your data is actually just samples from some distribution you're interested in, and now you're trying to estimate that distribution. And as dimensionality gets higher, that can become very difficult. So it's kind of an interesting problem how to do that in thousands of dimensions. And the final kind of problem that we deal with in machine learning, which is really important, is reinforcement learning. And I don't know if you've heard about things like AlphaGo that beat the best human players just a few years ago. AlphaZero, or DeepMind's other amazing reinforcement learning system, which was learned to play Atari games at human levels. These are all examples of reinforcement learning. And what makes them different from supervised learning is that in reinforcement learning, although you do get a reward, you don't get a reward for everything you do. So there will be an agent, there'll be something, some kind of algorithm that's acting in an environment, and every once in a while it will get a reward. So most of the time maybe nothing will happen, but then it'll occasionally get a reward. So for example, if you're playing chess, you might not get a reward until you either win or lose the game. And the question is, how do you build a system that with just that sparse information, whether you won or lost the game, can figure out how to play chess? And amazingly, this can be done, and it was originally done for backgammon in the 90s, and now it's been recently been done with these amazing reinforcement learning algorithms from DeepMind for other games like Go, these Atari games, etc. So this is a really important aspect of learning, but it's not one that he's going to talk about much in the book. So we're going to be focusing much more on supervised learning, unsupervised learning. So yeah, so those are kind of the big categories. And yeah, so then he kind of finishes off the section by just saying that the whole point of this whole introductory chapter is to introduce kind of some of these basic concepts that are going to come up over and over again in the book, and then also to have introductions to these three tools: so probability theory, information theory, and decision theory. And the kind of the interplay of these is what's going to help us solve these machine learning pattern recognition problems in a principled way, and kind of tackle lots of these really interesting tasks in kind of a principled way that will hopefully give good results. Great. So that's kind of what this introductory section was all about.